Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 2 of our unit Dual Nature of Radiation and Matter. In this session we are going to discuss about the wave nature of matter. So let's begin with the wave nature of matter. The nature of light shows up in the phenomenon such as an interferences, diffraction, and polarizations. On the other hand, in photoelectric effect and Compton effect, which involve the energy and momentum transfers, radiation behaves as if it is made of the bunch of the particles, and this bunch of the particles we know and we call as the photons. Whether a particle or a wave description is best suited for understanding an experiment depends on the nature of the experiment, that this wave, this matter behaves as a wave or it behaves as a particle. In certain they behave as a wave, and in certain experiments they behave as the particle. So this is the dual nature, this is the two nature of a matter. Mechanisms of light by the eye lens is well described in the wave picture, but its absorption by the rods and cones, when we are going to absorb the image, or we are going to absorb the information, this absorption by the rods and cones of the retina requires the photon picture of light. In 1924, the French physicist, who is the Louis Victor de Broglie, put forward the bold hypothesis that moving particles of matter should display wave-like properties under suitable conditions. So basically, the de Broglie has said that all those particles should be having a wave-like properties under suitable conditions. Now, if so, that means if radiation has a dual nature, that means the wave and particle nature, the particles of the nature need not also exhibit wave-like character. Now, let's back to the D what de Broglie has said. According to the de Broglie, he said that, and he proposed that the wavelength lambda associated with a particle of momentum p can be given as that lambda is equals to h by p, and this p could be replaced with the m weights, while p is the momentum of the particle, m is the mass, and v is the velocity of particle. Yes, m is the mass and v is its speed. The above equation, it's lambda is equals to h by p or h by mv, is known as the de Broglie relation, and the wavelength lambda of the matter wave is known as the de Broglie wavelength, where Planck's constant h, it relates this de Broglie wavelength and de Broglie it's a momentum of a particle. It is interesting to see that it is also satisfied by a photon. So for a photon, when I say it is a photon, we can write like this: it's a p is equals to hf by c. And if p is equals to hf by c, if I write it's an h by p, it's an h divided by p, that would be equals to c by v. And if I write it's a c by f, then it would be a lambda. So it's a, that means a lambda is smaller for a heavier particle. It is something like this: it's a lambda is equals to h by p. If mass is higher, then the lambda is lower. Or more energetic particle, let's say if frequency is higher, then lambda should be the lower. So that is the de Broglie wavelength of a photon given by the above equations equals the wavelength of the electromagnetic radiations, of which the photon is a quantum of energy and momentum. So in fact the thing is that lambda is equals to h by p could be used either it is a wave nature of matter or it's a particle nature of radiation too, because as we have seen that this is being satisfied by a photon as well. And for the wave nature or for the matter, we have already proved it, and de Broglie have defined it for them, for those particles only. So lambda is equals to h by p is available for everything, whether it would be a photon or whether it would be a certain matter waves. I hope this is clear. Is it clear? Great. Now let's take one example, that whatever the de Broglie suggested, that every moving particle should emit a certain wavelength from its body. So does it mean that if we are running, if we as a person are running, do we radiate anything from myself? Let's have a look. And if we are radiating something, then why can't we see it? Let's suppose we have seen the cars are running, we have seen that trains are running, we have seen the lot of things in motion. Then why do we see its motion as an wavelength? Why do we see that this amount of wavelength is radiated from the body? Let's take an example. Probably this might get clear your ideas. The de Broglie wavelength of a ball of mass, mass is 0.123 kg, and it is moving with a speed of 20 meter per second. I need to calculate the wavelength emitted from this. Look at this. This is 20 meter per second, which is not a smaller number. I hope you understand this. Have you? Yes. If you convert into kilometer per hour, you will find probably the actual the actual capability of it. Yes. So let's first calculate the momentum. Mass, it's a 0.12 kg, 0.123, and the velocity, it's a 20 meter per second. So this is 2.40. It's a 2.40 kg into meter per second. And if I need to calculate, if I need to calculate lambda is equals to h by p, then this h could be 6.63 into 10 to the power minus of 34. Divide by this momentum, it's a 2.40. If I solve this, it's 2.76 into 10 to the power minus of 34 meter. Now let's understand this, that this is the 10 to the power minus 34, and this is the wavelength which we cannot sense it. So if a moving particle radiates a wavelength from its body, my answer should be yes. Do we or can we feel it? My answer should be no. I hope you understand this, because this is a wavelength having very shorter wavelength. I hope this is clear. It's a 10 to the power minus of 34. Yes. So every moving body radiates certain wavelength from its body, that is for sure. But even that is sure that this wavelength is not going to be observed by us as a human being. I hope this is clear. Yes. So if this was the standard relation, that lambda is equals to h by p, and while I can replace p by the m into v, let's replace this for every other applications too, and let's check what are the formulas I have received. So on the other hand, in the subatomic domain, the wave character of particle is significant and measurable, as we cannot see that measurable in the human being or in the living objects. That, let's check it out. Let's suppose I am having the kinetic energy, and that kinetic energy could be given as q into v. If my charge particle is electron, then I could write its a kinetic energy is equals to electron volt multiplied by v, while v, it is the potential, difference. So if I am having kinetic energy which is equals to half mv square, this could be written as p square by 2m. So from this p is equals to under root of 2m into k, while kinetic energy, it is equals to e into v. So this is under root of 2m into ev. From this the de Broglie wavelength lambda of the electron could be given as this is lambda is equals to h by p. And if I want to replace this p, that would be equals to root of 2 into m into k. And to replace this k, it's a h by root of 2m into ev. Yes, this is the wavelength. This is the wavelength. Now, if I replace the numerical values of the h that we call as a Planck's constant, mass and mass of the electron and the charge of the electron 1.6 into 10 to the power minus 19, what we are getting is lambda is equals to 1.227 by root volt. Yeah, or you should remember this, it's a 12.27 divided by under root of volt into Armstrong. This is one of the favorite questions of the examiners. They will ask this. They will ask this for sure, definitely. So please do remember this and noted it down. It is lambda is equals to, it is the lambda is equals to 12.27 divided by root of voltage in the Armstrong. I hope this is clear. Is it clear? Is it? Are you sure? So everything is clear up till now, and everything, yes, no, yes, correct. So let's do one of the questions based on this. If an electron has passed through a potential difference of 144 volt, find out wavelength emitted. So what I need to do is, it's a lambda which is equals to 12.27 divided by root of voltage. It's a root of potential difference. So this could be, it's a 12.27 divided by root of voltage, it's a under root of 144, it's a 12. So this is 12.27 divided by 12, approximately 1 point something, but in Armstrong. This would be the lambda, this would be the wavelength emitted. I hope this is clear. So this can be done very easily, provided we know this relation. Otherwise it was bit typical. I hope you understand this, because how this has arrived is something like this, that we have the relation, it's a lambda is equals to h by m into v, while I have replaced this momentum by, it's a kinetic energy into 2m, and I have replaced this kinetic energy with the q into v into 2m. So if even I know this procedure, I need to put up the value of h, 6.63 into 10 to the power minus 34. I need to put up this value q as well, which is 1.6 into 10 to the power minus of 19. I need to put up the value of m, which is 9.1 into 10 to the power minus of 31, and then I need to solve this, which is not possible at all, because all the figures are very big numbers. I hope this is clear. Yes, when I say very big numbers, I mean they are very calculative numbers. So this will take a lot of time if I don't remember this. So please do remember this. Please do remember this. This will help us to get this done very quickly. I hope this is clear. Is it clear? Is it correct? So let's back to it. So where we, when we were discussing this, it's a lambda is equals to h by mv, and this is equals to 12.27 under root of volt Armstrong, where v is the magnitude of accelerating potential. Now we know this. So for a 120 volt accelerating potential, this can give a lambda of 0.0112 nanometer, or that could be converted to as a Armstrong very easily. This wavelength is of the same order as the spacing between the atomic particles in crystals. So this suggests that that matter waves associated with an electron could be verified by the crystal diffraction experiments, which is analogous to the X-ray diffractions. And the matter wave picture elegantly incorporated the Heisenberg's uncertainty principle. And in 1929, the de Broglie was awarded the Nobel Prize in Physics for his discovery of the wave nature of the electrons. He has been won the Nobel for this research. Now, let's focus on the Heisenberg's uncertainty principle. According to this principle, it is not possible to measure both the position and momentum of an electron at the same time exactly. He has derived this, or he has given this statement for the electron, but this is true for any other particle, that you cannot measure exactly or precisely position and momentum both. You could have any one of them. There is always some uncertainty in the specification of the position and some uncertainty in the specification of the momentum. The product of this, it's a delta x and delta p, is of the order of h. Well, h dash is equals to h by 2 pi, and the above equation allows the possibility that delta x is 0. That means the change in position is 0. That means if you have identified the position accurately, then it is possible. But there must be certain situation that, but then delta p must be infinite in order that the product is non-zero. Similarly, if delta p is 0, let's suppose you have defined the momentum very precisely, that means their change is 0, then delta x must be infinite. So, ordinarily both delta x and delta p are non-zero, such that their product is of the order of h. Now let's suppose that if an electron has a definite momentum p, if it is having a definite momentum p, it means its delta p is 0 because change in momentum is 0. So by the de Broglie relation, it is having a definite wavelength. So a wave of definite wavelength, which we call as a single wavelength, extends all over the space. So by Bohr's probability interpretations, this means that the electron is not localized in any finite region of space. That is, its position uncertainty is infinite because momentum is 0. Oh, sorry, change in momentum is 0. If change in momentum is 0, that means that delta x must be an infinite, which is constant with the uncertainty principle. So in that case, delta x is not infinite, but it is having some finite value depending on the extensions of the wave packet. So by the de Broglie relation, then the momentum of the electron will also have a spread and uncertainty of delta p. That means when I say that it is having a fixed volume, no, it is not like that. Even momentum would be having a certain variations. Only then these things can be possible. So it can be shown that wave packet description together with de Broglie relation and Bohr's probability interpretation reproduce the Heisenberg's uncertainty principle exactly. So from the de Broglie's relation and the Bohr's probability interpretation, we could we could reproduce the Heisenberg's principle. Do you clear with this? Are you sure? Great. So let's work for the certain quick questions. It says that the waves associated with the moving material particles, the waves associated with the moving material particles are known as they are the meta waves. Yes. De Broglie waves, yes. Photons, no. So correct answer would be both A and B. Next, the de Broglie wavelength. The de Broglie wavelength is independent of the blank and the nature of the material particle. Yes, it is a lambda is equals to h by m into v. So it depends on the m, it depends on the velocity, it does not depend on the charge. I hope this is clear. This is clear. Are you sure? Great. So now let's look at the Davidson and Germer experiment. The wave nature of electron was first experimentally verified by the C.J. Davison and L.H. Germer in 1927, and they were independently by the G.P. Thomson also did this in 1928, who observed the diffraction effects with the beams of the electrons scattered by the crystals. So what they were supposed to be done is that this is the heating filament, and when this are the heating filament, they are the considered as the source of an electrons. And here we have the accelerating anodes. That means we have connect this with the supplies of a voltage source, so that I can change the potentials. And so from here electrons will be emitted, and this electrons will pass through this region where potential difference has been applied, so they are basically accelerated, and they are going to hit the nickel target. When they are going to hit by the nickel target, they are going to be, after hitting with the target, they are going to scatter in certain directions. And to measure this scattering, or to measure this deflection, or I should say to measure this diffraction, I am having a movable detector which can sense it and which can measure this angle theta. And from that we can came to our conclusion. So let's look at this. It consists of an electron gun which comprises a tungsten filament F, which is coated with barium oxide, and it is going to be heated by a low voltage power supply. So electrons emitted by the filament to a desired velocity by applying suitable potential or voltage from a high voltage power supply. The beam is this beam that has been developed from the filament is made to fall on the surface of a nickel crystal. And from this the intensity of the electron beam scattered in a given direction is measured by the electron detector that we call as a collector. We have make such arrangements such that the detector can be moved on a circular scale and is connected to a sensitive galvanometer. While I have connected the galvanometer so that we can record the current too, and the deflection of the galvanometer is proportional to the intensity. It is the proportional to the intensity of the electron beam entering the collector. We have we have plotted the intensity I of the scattered electron with the angle of scattering theta, and is obtained for different accelerating voltage. This experiment was performed by varying the accelerating voltage from 44 volt to 68 volt. Please keep this in mind. This has been asked by one of the examinations in in probably AIPMTs were conducted at that time. They have asked this. So please do remember this. This experiment was carried out within a voltage range of 44 to 68 volt, and it was noted that strong peak appeared in the intensity I of the scattered electron for an accelerating voltage of 54 volt and at a scattering angle of 50 degree. So he has received a peak at 54 volt. The appearance of the peak in a particular direction, the appearance of the peak in a particular direction is due to the constructive interference of electrons scattered from different layers of the regularly spaced atoms of the crystal. So let's calculate this. This is lambda is equals to h by p, and from this we can have this, it's a 1.227 divided by root of volt. That's we have derived in the last theory only. It's we have received the peak at 54 volts, so it's a under root of 54, which will give me a lambda of 1.67 Armstrong. Even this has been shown here that at 54 volt The incident beam has been incident, and this angle, a scattered angle, is of 50 degree, so that there is an excellent agreement between the theoretical value and experimental obtained value of the de Broglie's wavelength. So Davidson-Germer experiment strikingly confirms that the wave nature of electron and the de Broglie's relation. So whatever the relation that has been derived and that has been suggested, that has been given by the de Broglie, is the same relation that Davidson and Germer received. So it gives a more kind of confirmation that yes, this is the practically viable relations too. I hope this is clear and you understand these things completely. Have you? Are you sure? Now, do you have any doubts? Is there anything? Is there? No? Great. Let's look at the quick questions. They say that de Broglie wavelength lambda associated with electrode for voltage is equals to 54. Its lambda is equals to 12.27 divided by root of voltage. So this is the wavelength. It's a 12.27 divided by root of the voltage. When I say it's a 12.27 divided by root of voltage, this voltage is equals to 54. And if I put up the value, it's a 0.167 Newton into meter. Next, Davison-Germer experiment confirms that the wave nature of electrons and the de Broglie relation. Yes, he confirms the wave nature and de Broglie relation. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's discuss de Broglie de Broglie wavelength associated with the charged particles. We have this relation that kinetic energy of the any particle could be written as energy is equals to half mv square, and this energy could be given as a q into v, where v is the potential difference. A momentum of the particle p could be written as p is equals to mv, and this is equals to root of 2me, and this e could be given as q into v. This is root of 2m into qv. So we understand that the de Broglie wavelength associated with charged particle lambda, that could be given as lambda is equals to h by p, and if I replace this p with under root of 2me, this is equals to h divided by under root of 2me, while this e could be given as under root of q into v. So this is equals to lambda is equals to h divide by root of 2m into q into v. So so if these are the master relations to find out the wavelength of any charged particle. We have derived for certain particles too. Let's have a look. So for an electron, the master relation was, look at this, it's a lambda is equals to h divided by root of 2m into q into v. So for an electron, mass of the electron is 9.1 into 10 to the power minus of 31 kg. Q is the 1.6 into 10 to the power minus of 19 coulomb, while H, it's a Planck's constant, it's a 6.62 into 10 to the power minus of 34 joule into second. So if I replace all these values, kept V intact, it would be a 12.27 divided by root of voltage Armstrong. That means lambda is inversely proportional to the potential difference applied. It means higher the potential difference, lesser would be the wavelength. That is what we call as an higher the energy, lesser would be the wavelength. This was for electron. Please do remember this, as well as please have a note of this. Next, for protons, only the thing that has been changed will be the mass of the proton, which is equals to 1.67 into 10 to the power minus of 27 kg. So de Broglie wavelength associated with proton is, that is equals to lambda of proton would be equals to 6.62 into 10 to the power minus of 34 divided by root of 2 into 1.67 into 10 to the power minus of 27 multiplied by 1.6 into 10 to the power minus of 19 into volt. If I replace this with the value, it would be a 0.286 divided by root of potential difference. Please have a note of this. Same way for a deuterium, it's a 2 into 1.6 into 10 to the power minus of 27, and charge of the deuterium, it is the same as the electron or proton. It's a 1.6 into 10 to the power minus of 19. So if I put up the value, I get this value. It's a 0.202 divided by root volt Armstrong. I hope this is clear. And next, for the alpha particle, for the alpha particle, that is equals to charge of the alpha particle. This is equals to 2 into 1.6 into 10 to the power minus of 19 coulomb, and the mass of the alpha particle, which is equals to 4 multiplied by 1.67 into 10 to the power minus of 27 kg. So if I replace this with the values, then I could have this. It's a 0.101 divided by root of voltage. I hope this is clear. Is it? Is it clear? Have you noted it down? Have you noted down all these values? Do you? Do you? Great. So let's, if proton and alpha particle has passed through a potential difference of 400 voltage, find out their wavelengths. So this is the question. How will you solve this? First, they have asked about the proton. Let's have a look. For the proton, this will be equals to 0.286 divided by root of voltage. So it's a lambda of proton, it's a 0.286 divided by root of voltage, while potential difference, it is a 400 volt. So this is equals to 0.286 divided by 20, and when it is 0.286, when it is 0.286 divided by 20, this would be is equals to 0.0143 Armstrong. This is the lambda, this is the wavelength of the proton. And now let's calculate, the wavelength of the alpha particle too. It's a lambda of an alpha particle, that would be is equals to 0.101 divided by root of voltage. This is equals to 0.101 divided by 21, and if I do this it would be equals to 0.101 divided by 20, which would be a 0.00505. It's a 0.00505 Armstrong. So this is very easy if I know this. I hope this is clear. Even we have discussed this when we have done a numericals based on the electron. So this all are very easy. This all are very easy provided I know this relations. If I don't know this relation, then this are very big numbers, and that cannot be done, or that does not allow us to do it very easily. I hope this is clear. So please, this is requirement. This is to be remember. Please remember this. I hope this is clear. Is it clear? Great. Now let's discuss the de Broglie wavelengths associated with uncharged particles. So if the particles does not contain any charge, what would be the situation? First, it's a kinetic energy of the uncharged particle. That kinetic energy would be given as E is equals to half mv square. And when I say it's an half mv square, this is equals to p square by 2m, where m is the mass of the particle. V is the velocity of the particle and P is the momentum of the particle. From this, it's a velocity of uncharged particle that is equals to root of 2e by m. And from this, I am having the momentum which is equals to m into v, which is equals to root of 2me. So, so it means wavelength associated with the particle, that would be equals to lambda is equals to h by p. While I replace p with the mv, this is equals to h by mv, and this could be given as h by root of 2me. So it is something like that, that kinetic energy of the particles in terms of its wavelength, the wavelength, it would be E is equals to h square by 2 into m into lambda square. And this is the situation in certain electron volt. So if I want this for a neutron, then it could be given as it's a 1 point mass of the neutron, it's a 1.67 into 10 to the power minus of 27. So from this it's put up the value and try to get it done. This is equals to 0.286 Armstrong. This is 0.286 divided by root of E Armstrong. I hope this is clear. Is it clear? Are you sure? Are you sure? Great. Now let's discuss a certain logical parameters regarding this dual natures. Let's have a look. That let's suppose this, we are going to discuss this in a form of a questions too. That let's suppose if a photon and an electron, if a photon and an electron have got same de Broglie wavelength, they have received same de Broglie wavelength, which then which one is having higher energy? So what do you think, if photon and electron is there, and if they both are having the same de Broglie wavelength, they have received the same de Broglie wavelength, then which one is having higher energy? How will I do this? How could I? What do you think? So we could think this in like this manner, that let's suppose a total energy of photon is E1 is equals to hc by lambda, while total energy of electron, this is equals to E2 is equals to, we could write it's a mc square. And while I write mc square, this could be written as it's a h by lambda v into c square. I have just replaced this m, it's a lambda is equals to h by mv. Yes, so I have replaced this. I hope this is clear. Now let's take the ratio of the total energy of electron to the total energy of the photon. So if I take a ratio, it would be a E2 by E1. So it would be a hc square by lambda into V multiplied by h by lambda into C. So this h and h has gone, and this c is gone, and I have been left with the C by V. I hope this is clear. Is it clear? Yes, this was the lambda by hc. So lambda by hc. Yes. So this has gone. This has gone. Yes. So I have been left with the only the C by V. As I understand that this is C is the speed of light in air or vacuum, which is the maximum possible value. So that means C is greater than V. That means this number would be having always a value which is greater than 1. And if it is greater than 1, that means E2 is greater than E1. Now, in my case, E2 would be of total energy of electron and E1 would be the total energy of photon. So, total energy of electron is greater than the total energy of photon having same de Broglie wavelength. I hope this is clear. Very logical and very effective. Yes, I hope this is clear. This is clear. Great. Do you understand this? Do you understand this? Are you sure? Great. Now, let's discuss on next. Suppose if I have been asked that, find out de Broglie wavelength of a gas molecule of a gas molecule of mass m at the absolute temperature T, at absolute temperature T. So how will I do this? The situation would be, it is lambda, this is equals to h by p, and when I say it's a lambda is equals to h by p, this would be lambda is equals to h by m into v. While I say lambda is equals to h by mv, this is equals to h divided by root of kinetic energy multiplied by 2m. I hope this is clear. Yes, it's a kinetic energy is equals to p square by 2m. So p is equals to under root of kinetic energy into 2m. Now for the gas molecules, for the gas molecules, this kinetic energy will be equals to 3 by 2 kb into temperature. So if kinetic energy is equals to 3 by 2 into kbt, what I can have is that lambda is equals to h divided by under root of 3 by 2 kbt multiplied by 2m. This 2 has gone, and this is equals to h divided by root of, it's a 3 kbt into m. This is the wavelength. So it's a wavelength of gas molecules. That means wavelength of gas molecules is given as lambda is equals to h by root of 3 kbt into m. So its variation is 1 by root of m if temperature is constant, and its lambda is 1 by root of t if mass of the gas is constant. That means gas is particularly constant. I hope this is clear. So higher the temperature, this means higher the temperature, lesser would be the wavelength, as well as heavier will be the mass of the gas, lesser will be the wavelength. I hope this is clear. Is it clear? Is it clear? Are you sure? Great. So can we do one of the question based on this? Can we do one of the question of this? Let's have a look. Find out ratio of de Broglie wavelength when gas molecule having mass m at two different temperatures of two different temperatures of 127 degrees Celsius and 227 degrees Celsius. I need to find out the ratio. So mass is constant, only the temperature which is changing. So it's a T1 which is equals to 127 degrees Celsius, but it depends on the absolute temperature. So it's a 127 plus 273. This is equals to 400, and the second temperature which is equals to 227 degrees Celsius, which is 227 plus 273. This is 300 plus 200, which is equals to 500. So from this, the situation would be lambda 1 by lambda 2. This is equals to root of T2 by T1. From this, it is under root of 500 divided by 400. This has gone, this has gone, and this is equals to root of 5 by 4. This is lambda 1 by lambda 2. I hope this is clear. So it's a lambda 1 by lambda 2 which is equals to root of 5 by 4. This is the ratio of their wavelengths. I hope this is clear. Is it clear? Is it clear? Great. Now let's discuss the next applications. That if if electron is orbiting around third orbit, find out number of de Broglie wave associated with it. How will I do this? What could be done? So what I understand is that they have given that electron is orbiting around the third orbit, and I need to find out the de Broglie's wave associated with it. So what I understand is that it would be always a 2 pi r is equals to n lambda, or it would be something like this. It's a n is equals to 2 pi r by lambda. I hope this is clear. And according to the de Broglie, it's a lambda which is equals to h by mv. It's a n equals to 2 pi r divided by lambda which is equals to h by mv. I hope this is clear. So from this, it's a 2 pi h multiplied by this mvr, which is an angular momentum. So from this n is equals to, it's a 2 pi by h multiplied by mvr. Mvr can be written as nh by 2 pi according to the Bohr's postulate. So this is the relation, this is the relation, this is 2 pi, this is 2 pi, this is h, this is h. So this would be equals to n, and this n is the orbital number. Shall I change the let's call this as an m. I have just changed the notation so that it does not create any confusion and panic. So this is m. It's at what we call as a principal orbital number, and this is number of waves. So as n equals to m, and electron is orbiting in the third orbit, so it is having three waves associated with it. I hope this is clear. Is it is it clear? Are you sure? Do you understand this? Have you? Have you got this? Are you sure? Can we do this? Great. Now let's look and moving forward to the next. The question is, if an electron is moving in the first excited state, find find de Broglie's wavelength. Find de Broglie's wavelength associated with it. How will you do this? So for this, I understand again, do the same thing. It's a lambda is equals to h by mv, and when it is equals to h by mv, this is equals to root of kinetic energy multiplied by 2m. If it is something like this, then lambda is equals to h by under root of kinetic energy, which is equals to, which is equals to here. It's an, if you remember this kinetic energy, it's a 13.6 by n square into z square. Yes, let's call this for the hydrogen atom. if if z is equals to 1 over here, then this is equals to 13.6 divided by n square multiplied by 2m. This is just the kinetic energy. I hope this is clear. Is it clear? So if I replace this value, what I am having is the 12.27 divide by root of 13.6 by n square Armstrong. This is the situation. I hope this is clear. Is it clear? Is it? Great. So now let's put up the value and get the answer. It's a lambda which is equals to 12.27 divided by root of 13.6 by n square. This was the situation, and my electron was orbiting in the first excited state. So when it is in first excited state, that means this n equals to 2, and if this n equals to 2, this is lambda which is 12.27 divided by root of 13.6 by 4, it's a 3.4. This is in Armstrong. I hope this is clear. This is clear. Does it? Are you sure? So now can you do this kind of questions? Are you? Are you sure? Do you have any doubts? Is there anything? Is there anything? No? Great. Let's work for the next question. The question says that when the momentum of photon is changed by an amount of p naught is changed by an amount p naught, the the corresponding change in the de Broglie wavelength, the corresponding change in the de Broglie wavelength is found to be is found to be 0.25 percentage Find out. Find out original momentum of the photon. How will I do this? So, what I understand is, according to the de Broglie, it's lambda which is inversely proportional to the 1 by p, and as it has been changed by 0.25 percentage, I can use the relations of the errors as well. So it is the delta p by p that is equals to minus of delta lambda by lambda, and from this it's p naught by p, that is equals to, it's a 0.25 divide by 100. So from this it's a p which is equals to 400 times of the initial, it's a 400 times of p naught. I hope this is clear. Is it clear? So let's wind up this session over here. This was all about the matter having the wave nature and having the particle nature, as well as we are completing the dual nature over here. Yes, it is a very short unit of having 2 lectures only, so please go through this, please revise it. It is having capability to deliver at least one question in the, either it would be a neat examination or it would be an JE examinations. And even the relations are very limited, even the applications are very limited, so this can be done very easily. Please go through it thoroughly. Please do as many questions as possible, because this can be done very easily. Thank you. Have a good day. Take care. Bye bye.